This video is on velocity time graphs. So at this point you should have looked at the equation for acceleration. So acceleration is the change in speed or velocity divided by time. The units of acceleration are meters per second squared. Speed is obviously meters per second, and time is in seconds. Now, we quite often write this equation as acceleration is v minus u divided by t, and v is the final speed or final velocity that an object reaches, and u is the initial or starting speed or starting velocity. Remember, the difference between speed and velocity is speed but with a direction. So this is the equation that you've done before. Now this relates directly to a velocity time graph, or a speed time graph. So with our velocity time graph, so I've got time and I've got speed or velocity. Now, when you have an object that is stationary, so that an object that is not moving, on a velocity or speed time graph, if they're stationary, that means they don't have any speed, they're not moving. So what that would look like is a flat straight line, but it must be at zero, because that represents zero speed. So that actually represents the graph for an object that is not moving. So if I have a straight line here, for example, you could imagine that this is 10 meters per second. So you can see that my object now, its speed is not changing. So on a velocity time graph, a flat line represents constant speed. And I want to stress how this is different to a distance time graph, in which a constant speed is represented by a straight diagonal line. So that means, what does a straight diagonal line represent? So if I have a line like this on my velocity time graph, what's now happening to my speed as time is increasing is that it is increasing. And increasing speed, we should remember, is acceleration. And more than that, because this is a straight line, this represents constant acceleration. Now that also means that if I've got a straight line going up for constant acceleration, I can think about, well, what would deceleration look like? So deceleration is obviously when a speed is decreasing. So deceleration would be a straight line going down. That would be constant deceleration. And then if the line is curving, now what that means is that my acceleration is now changing. So if I have a line that curves upwards like this, my acceleration, which is represented by any upward line, keeps getting steeper and steeper and steeper. So this would now represent increasing acceleration. And a curve flattening out would represent decreasing acceleration. So remember that those shapes are all very different to a distance time graph, and you must appreciate them separately. So now I can do calculations with my velocity time graph. So if I have a very simple velocity or speed time graph, time in seconds, velocity in meters per second, and I'm going to add some speeds, so I'm going to have 5, 10, 15, 20, 25. Just going to add some time in seconds. So if I've got an object now that is travelling with constant acceleration, like so a straight line, I can calculate the gradient of this line. And the gradient of this line, remember, gradients are always the change in y divided by the change in x. Now in this particular graph, y is the change in speed, and x is going to be the change in time, which we saw previously as our equation for acceleration, the change in speed divided by time. So the gradient of a velocity time graph or a speed time graph is equal to acceleration. So to calculate it for this example, I have to work out the change in y. So I look at how tall my line is, and I look at how far along the x-axis it goes. So along the y-axis, it's gone from 0 to 25, so the acceleration would be 25 minus 0, or 25. And then here it's gone again from 0 up to 4 seconds, so the change in time is 4 minus 0, which is obviously 4. So I'm doing 25 divided by 4, which is going to be 6.25 meters per second squared. So that would be my acceleration. Now, acceleration is only one thing that I can work out from a speed time graph or a velocity time graph. There's one other important thing that I can work out, which is the distance that the object has travelled. And this goes back to our basic equation for speed is distance divided by time. So distance is speed multiplied by time. So the distance travelled by this object is the area represented under the graph that I've just shaded in here. This area represents the distance travelled because the speed is increasing. If the object was travelling at constant speed, for example at 25 meters per second for 4 seconds, if it travels 25 meters every second for 4 seconds, it's going to travel 100 meters. Now, because the speed is increasing, it's not going to travel 25 meters in the first second. So what I have to do for this now is I have to work out the area always under the line. So if I've got a triangle, remember we work out the areas of triangles by doing the base times the height, which is going to be speed times my time. But then because it's a triangle, I have to remember to divide it by 2. So the distance travelled by this object is going to be 25 times 4 divided by 2, which if you put into your calculator will be 50 meters. So this object has travelled 50 meters. If we just do one more example. So I just need another velocity time graph. So I'll make it nice and simple again. 1, 2, 3, 4, and 5, 10, 15, 20, 25. Now let's imagine that we have an object that has travelled at constant acceleration, then travelled at constant speed, and then undergone constant deceleration, like this. So first of all, I can work out the constant acceleration for this part of the graph by reading off from the x and the y axis. So the change in the y axis for this part of the line is from 25 to 10, so the change is 15. So the acceleration for this bit is going to be 15 divided by 2, which is my change on my x-axis. So that's going to be 7.5 meters per second squared. This part here is constant speed, so at that part the acceleration is simply 0 meters per second because it's not increasing or decreasing its speed. And here it's now traveling at constant deceleration, so I do the same thing. So we can see that the change on the y-axis is now 25, but it starts at 25 and ends at 0. So if we use our equation that we did, acceleration is final speed take away initial speed divided by time. The final speed is 0, the starting speed is 25, so this will actually be, acceleration is minus 25 because it's going downwards, and then it does this in a time, if we make that 5 seconds, of 1 second. So it's actually got an acceleration of minus 25 meters per second squared. Sorry that you can't see that, I'll just write that there. So acceleration is minus 25 meters per second squared. Now, acceleration is only one thing we can calculate. We can also work out the distance travelled. Now, to do this, I have to break the graph down into several parts. So, first of all, if I work out the area of this rectangle in the centre, it's simply going to be 25 times 2. So that's going to be 50 metres for this part of the graph. Now, if I work out this area, this triangle, it's going to be 25 times 1 divided by 2. So you should be able to see the height times the length. So that's going to be 12.5 metres for this part of the graph. And then I've got this part. Now what I need to do here is break this into 2 bits, a triangle and a square. So I have 10 times 2, which is 20 metres. And then for this bit I've got 15 times 2 divided by 2 because it's a triangle. So that's obviously just going to be 15 metres. And then I add them up, so it's going to be 15 plus 20, which is 35, plus 50, which is 85, plus 12.5. So the total distance travelled in this graph is 97.5 metres. It should be understood that the total distance that's been covered is 97.5, but the objects, because this is a velocity time graph, it takes into account direction. This object hasn't changed direction at any point because it's always in the positive part of the axis. It would only change direction if it became negative, if it came down here. So you imagine -1, -2. So this object has simply accelerated, travelled at constant speed, then decelerated. So it's travelled 97.5 metres from its original starting point. So for velocity time graphs, remember, you need to be able to calculate the gradient, which is the acceleration, and the area under the graph, which is the distance travelled. Both of those skills are really important for your first assessment, so make sure you study them carefully, and also make sure that you can interpret the various shapes for velocity or speed time graphs. Just one final point about the difference between speed and velocity time graphs. So if I have a speed time graph, it does not take into account direction. So for example, if I have a ball and I throw it upwards to a certain height, it will then get to that certain height, it will then stop in the air momentarily, and then will fall back down to where it started. So imagine I'm throwing a ball up in the air. On a speed time graph, if you think about what happens, so it starts travelling fast and as it leaves my hand, but straight away starts to slow down until we know that at this point the speed is 0. So there has to be a point when the speed crosses the 0 axis and it slows down, so we can see that's constant deceleration. So for a speed time graph, that would be like so. and then it's speeding up again, but in the opposite direction. On a speed time graph, because it doesn't take into account direction, that doesn't make any difference, and it's just going to be speeding up at with constant acceleration again. On a velocity time graph, that's slightly different, because now the first part of the graph will be identical, but because it does take into account direction, so remember at that point the speed is 0, rather than just the speed increasing in the positive direction again, it's increasing in the other direction, so it would carry through like so into the negative part of the graph, which represents the other direction. So remember, speed is an example of a scalar quantity, and velocity is an example of a vector quantity. Scalar quantities have magnitude only, they only have size, and vector quantities have direction as well.